Hey guys, so this video is going to be a design review. I haven't gotten a lot recently, so definitely if you're interested and you have something you want me to review, please send it in. I'll have the link below. It's definitely more of a more simplistic review than I would normally do, but it actually has a few different parts of it that ironically I was going to do a video on, and I still might do in more detail. So I think it might be kind of an interesting one to look into. So basically here is the schematic, and like I said, it's quite simplistic. What it is this is a Pi 0 header. So it's going to be like the top board. I think in the Pi world they call it like a hat, I think. So there's a Pi hat. It has a power supply from 12 volts. The 12 volts will be used to power some external LEDs. The 12 volts also goes through a 5-volt linear regulator, which will be dropped down for the Pi. The Pi controls the LEDs via a Darlington pair array Darlington transistor array. What it's used for is, and I'll have a link in the description, I really didn't look into it much, but it's for like doing some light shows. There's I guess a Pi library that lets you do light shows with it and sync it to music, so pretty cool. I saw on their website you can do it for like Christmas lights. So I guess this is the version to do it with just 12 volt LED strips. I guess what I want to do is I want to start with, there's a few like glaring issues that I think pretty much would have to be solved, and then just some alternatives and just a few different considerations with any type of design where there's driving outputs. The first thing is, and this is something he had asked specifically on, was the fuse and diode configuration. So the first thing is, before I start with the power supply, rating fuses and everything, I always will add little notes to each power section. What is the like worst case power consumption, and then work my way back. For these LED strips, and they're basically just like little 12 volt strips that you can stick on or plug in anywhere. So they have the current limiting resistors. So they are essentially constant voltage. I found online is they draw around 250 milliamps. So we have 8 outputs at 250 milliamps. So our total power consumption is a max of 2 amps. He is supplying the 12 volts alternating pin by pin from the main 12 volt supply. So basically each positive end goes to the 12 volt, the negative end is sunk from the Darlington array. So the first thing that you can obviously see is he only has a 1 amp input fuse rating, so that obviously has to change or he'll be blowing fuses. So this is one of the things that I wanted to talk about specifically. I used to like kind of always put a standard input fuse on the board for safety. In more recent projects and seeing some of our projects and designs in the field, I've kind of changed my tune on that, because ultimately having an input fuse like this, it's not going to trip in any dangerous situation. And something we'll get to later in the video is having fuses on each output. Those are going to trip, or even if you don't have a fuse here, this array is current limited. So in order for that input fuse to blow, you would have to have every single output, every single thing on your board overloaded, which really isn't going to happen. So as just kind of a band-aid, putting an input fuse on every design, I've kind of changed my tune on that, and I don't do it as often. It's not required by most certifications like UL, which is another reason I've stopped doing it, because we've had a couple designs going through UL testing, with them being kind of the gold standard. If they don't do it, probably don't need to. With that being said, I still will use fuses quite often on the input side, but I use them in a different configuration and for a different reason. Again, this 1 amp won't work. So what I typically do nowadays is I will change this to, say, a 3 or 4 amp fuse, just to give yourself enough headroom. And the Pi, the reason I skipped the power consumption, I really couldn't find a good answer. From what I gathered, it was like a quarter amp max, which at 5 volts going to 12 volts, that's negligible. So we can essentially ignore this power consumption. If we do the input fuse at 4 or say even 3 amps, I would make this a PTC fuse so it's resettable. Other issue and why I've stopped doing the input fuses just globally is what happens when it trips. If this is something that you sell, now the entire board's shot. And if it wasn't protecting from a hazardous condition, you just bricked their entire board for no reason. Obviously, if there's a safety reason, that's fine. But if you put it too close to the limit and you're getting what are called nuisance trips, that's no good for anybody. So I've been starting to use PTC fuses, which are resettable. So if something goofy happens, they can just cut power, plug it back in, and it works. You'll notice on a lot of cheaper products, that's how they operate. If you put something in reverse polarity, it'll shut off and you're scared that you broke it. If you take the battery out and put it back in the right way, it'll work. So what they typically do, and this is something that I have started doing fairly often, is you reverse bias the diode like this. So now in normal operation, the cathode's higher than the anode, so nothing happens, nothing goes through here. You size your fuse to where in normal operation, it will never trip. It's not going to protect anything downstream, but the key is you flip the polarity. Now this is higher voltage, the anode is higher voltage than the cathode, and it conducts, trips your PTC fuse, instantly open circuits this, and saves the rest of your circuit. One thing I've also been trying to stress, like in the ESD video and now on this, is for a lot of things on circuits, there's no one right or wrong answer. There are so many ways to protect a circuit from reverse polarity. You can do a crowbar circuit, you can do a integrated reverse polarity IC, you can do what he had, just a inline diode. They all work, some are better in certain situations. This I like, it's kind of a middle of the road price solution. It's not the cheapest, but it's not as expensive as a crowbar circuit, and it works very quickly and it's resettable. So that's why this is kind of like my go-to. The way that he had it with it just in series, unless it's a super cheap board, I will almost never do, is you're dropping power, you're dropping voltage over that diode, so you're losing power even when it's operating normally, which I don't like. A PTC fuse barely has a resistance, so you are losing power, but usually it's negligible. So that's the first thing that I would change. The next issue is he's using a linear regulator, which a linear regulator, as the name suggests, drops the voltage linearly, so it dissipates that voltage as heat. Calculation to do this is pretty simple. It's P equals IV. We know that the current that the Pi is going to be drawing maximum is, say, 0.25 amps times, now our voltage that is going in is 12, our voltage that is going out is 5, and when you do that calculation, you get 1.75 watts. Now, take this with a grain of salt. I don't know what the Pi power consumption and how he's going to be using it is. If it's half of that, now you're under a watt of power. But if you're expecting it to be in this range, I don't know this exact what chip he's using. He's using a SOT 223. So that's not a super good power dissipating footprint. So at almost 2 watts, it would probably overheat. Now, if you can get a pretty big heat sink on it, it might be okay. But that is a super important calculation that anytime you're using any linear current control or linear voltage regulator, you have to take that into account or else you're going to burn up that chip. So options here would be, one, to switch it to a switching regulator, which I don't think is required. It would probably be overkill. I would just make sure and do some calculations or some real world tests ideally and see what this pi actually draws and I'm assuming that I'm wrong and it's going to be less than 250. If that's the case, then it should be fine. And then also consider using a different package. Now the next thing, he has a in-series diode. I don't exactly know what this is for. Maybe to prevent the pi from backfeeding onto this regulator. He has a note to not use a USB cable, so I'm assuming that he's not expecting it to be powered anyway. So I would assume that that diode can be removed. I don't know the specs on what specific, so it's a TI, maybe they have a spec that you can't have a output voltage applied without an input. That depends from chip to chip. Sometimes they don't say, sometimes they'll specify, and you don't want to have the output voltage higher than the input voltage. Maybe that's the case, but either way, if you can avoid having that series diode, you're going to dissipate less power, so it would be helpful. It plugs into the wall, so it's probably not that big of a deal, but something to consider. So everything here is what it is. It's just passing through. So now, powering these diodes, I honestly haven't seen, or two things. One, I've actually used this exact same Darlington array. We used it for a industrial control board. It had to control mechanical relays. Darlington arrays are super common for relay control, and what they do is essentially it's just a cascading set of transistors. So a small transistor triggers a bigger transistor, so you can get a really big gain from a single transistor appearance-wise. There are two internally. So it's really useful for syncing a large amount of current from a small input signal, but you really don't see them that much other than relay controls because typically MOSFETs are used nowadays. I've never seen a Darlington array used like this to control LEDs. I don't see anything here that is striking me that it wouldn't. The issue I can see is this is going to be used for lighting effects, flashing, on, off, maybe brightness control. It's probably not going to be fast enough. The big reason you use a MOSFET is because their switching speed is really as fast as you want it. You can spec it to whatever you need, where a transistor is inherently slow. You can use it in between the linear region or saturated. So it still might work, and I know why he's using this, solely because it's a single package with all 8 control lines. MOSFETs, you would probably have to use them individually, or maybe a 4 or 6 MOSFET array, and it would take up more space. So I get why he's doing it. I'm assuming it'll work, but that's something to consider definitely. One cool thing about this Darlington array is it has an in-series base resistor, so you can do exactly what he does and just power it straight from the Pi. I would check to make sure these pins can handle that much current. I don't really use Pis that much. I'm assuming it can, but that's another thing I would consider. But either way, that isn't really that important in my mind because it's just something you're going to have to test and see if it switches fast enough. What I'm more interested in is then, and this was a question that he had, is your output lines. And this is where, when it comes from a safety standpoint, I've kind of changed the way that I handle boards, and I focus more on this side for safety than on the input supply. I always try to think of is, again, the reason why a lot of this has changed recently is some of the stuff we've done with UL and how they test it. So essentially, if this was going to be something that UL would test, they would take sometimes it's literally just a screwdriver, they take a tool that will short output pins. So they will literally take a screwdriver and short these 2 pins out and run your product as it would be functioning. So what's going to happen? This Darlington array is technically limited to, I think, 500 milliamps. I could be wrong. If you trust this Darlington array to limit that current, you're probably fine. If you were to be using a standard MOSFET or something that doesn't limit the current, what's going to happen? Well, something has to limit the current. So it's either going to melt a trace. It's going to, if you have an input fuse, it might trip that, or it's going to overload something on your circuit. So what I have gotten into the habit of is when I'm doing a design on the outputs, I pretend I'm UL. I go through every output and say, okay, if this is shorted, what happens? And I have to have a good answer to that or I don't feel confident. So on this one, we can look at the data sheet for this Darlington array, which I'm not going to do because it either is limited or it isn't. If it is limited and it's limited at 500 milliamps, I would then make sure that all of these traces are rated for at least an amp, because I always like to do 2 times D rating. And if that's the case, then we're probably good. If they're not current limited fully, or it's current limited to a level that I don't feel confident with, then I put an inline fuse. Do you put a PTC fuse or a standard fuse? That's a tough one. Again, if someone is an idiot and happens to short this out, now their board's ruined. They have one output that doesn't work. Is that a deal breaker for your product? That's another thing to where there's no right or wrong answers. If you do a PTC fuse, you have the advantage of being able to reset, but we need 8 of them. PTC fuses are 2, 3, 4, 5 times as expensive. Now your device just got more expensive. You could also use a series resistor to limit the current, but now you're dissipating power and your LEDs aren't going to be as bright. You could do an inline, what's called like an E fuse, to where it's kind of like that Bourne's, it's actually pretty similar to that Bourne's chip that I showed in the ESD video, to where it's an electronic resettable fuse. That would have the same effect as the PTC fuse in that it's resettable, but more expensive. Again, there's no right or wrong answer. There's a bunch of different ways you can protect this output, and as long as when you're designing it, you can, and the way I do it again is I pretend I'm UL, stick a screwdriver in. As long as you're confident with your answer to that, should be good to go. And if it's something that you're going to be selling, I would test it. I would take your screwdriver, check all of your outputs. You can check your inputs. You can check anything on this board and see what happens. Because when you go through your board and you know for a fact what is going to happen when something bad happens, your board either just breaks, but breaks in a safe way, that makes you feel a lot more confident when this is going to be sold, and potentially people could be hurt, property could be damaged. Knowing that you've done everything in your power, that makes it a lot easier to be able to sell this. So there's my philosophical spiel over with on the outputs. That's really all there is with this design. He has a layout that's also with this. Again, it's such a simplistic layout. There's really not a whole lot here. The only thing that I can really say, and this is something he had mentioned, is where his ground planes are. It's not required, but for something like this, throw on a top ground plane. It's not going to hurt anything. So what you can do is just duplicate the bottom one and make the top plane ground as well. And that's actually something I saw in the new version of KiCad. You can have a single plane work on multiple layers instead of needing duplicates, which is awesome. And now if you do a top and bottom ground plane, you'll need to add obviously stitching vias to make sure top and bottom are connected, and don't do it how I'm doing. Put them on a nice grid, make it look pretty, make it look like you care. Other than that, again, there's really not much here. Here's the transistor array, and since these are these are surface mount, this is through hole. I don't know why you could get this way smaller if it was surface mount. So I would definitely switch that just to save some space. And then here are all of our outputs. He has them at a 0.2 millimeter trace, which is what, a 8 mil trace. Definitely would make those thicker. He has the 12 volts as a 20 mil. but the signal lines as a lot thinner, that defeats the purpose. There's going to be the same amount of current flowing through the signal as there is each individual 12 volt trace. I would probably make a plane or something over here for the 12 volt, or just make it a lot thicker. He has tons of room here to make this thicker to where you don't have to worry about any voltage drop, because what I'm thinking of is the two center 12 volts, because it is a daisy chained trace, even though it is from both sides, which is helpful. There's going to be a voltage drop going across here. The thicker the traces are, the less apparent that'll be. So you could either make this a pour or just a really thick trace and go around here, and then make sure to make the signal traces thicker. It's one of those things, if you have the space, make it thicker. Like, just make it thicker. There's no reason to have a thin trace unless you're at high speeds or impedance matching, stuff like that. It's always going to be more beneficial to have a thicker trace than a thin trace. Even for these, I mean, there's no need to make them thicker, but if you have the space, you might as well. And then obviously same with the input. He has the input 12 volts about as, let me see. He has the main input 12 volt trace, the same thickness as the 12 volts going to here, which doesn't make sense because obviously this 12 volt trace is going to be carrying the most amount of current of anything on the board. Same with that input ground, so it should essentially be the thickest thing on your board. I like how he has a plane here, but there should be a plane here. Other than that, it's a pretty simplistic board. I don't really see anything else that sticks out. Same with the schematic. Overall, other than the fuse and maybe looking at that voltage regulator, it seems like a pretty good design. I don't see why it wouldn't work. Just a few considerations with safety on the output, maybe the switching speed, but otherwise I think it should do great. So I hope you guys enjoyed this design review. Once again, if you have any reviews that you want me to, or any boards you want me to review, please send them in. And any other suggestions for future videos, please let me know, and I will see you in the next video.